Well, hello, everybody. Uh, we are continuing with our toy programming language. As usual, if you have any questions, put them in the chat in Zoom. I will answer either at the end of this talk, or I might make a pause like in the middle of it and answer your question. If there are any technical issues, also just write something in the chat and we'll be able to react to that. Okay, anyway, last time we looked at the parser and at the ways we can parse expressions, especially binary expressions. And here's what we ended up with. So this is a valid expression in our language. And today we are going to be looking at the AST, abstract syntax tree. Finally, because last time the parser, what it basically did, it went through our grammar and it just posted in the console what it saw, basically in terms of grammatic constructions. Now, the idea behind the AST is like really, really simple. It's not something advanced or anything. The idea is, well, we have the grammar and different kind of parts of a language are defined via other parts of the language. So we get this kind of nesting of grammatic rules. And the language structure itself kind of reflects it. So we have a hierarchy and nesting of different grammar rules. And we also have a hierarchy and nesting of different language constructions. Like expressions can have sub-expressions. They themselves are parts potentially of bigger things like statements, declarations, or whatever. And those in turn are organized in lists, like a function body or a global scope where you have all the declarations of different functions, variables, and what have you. So yeah, the AST just reflects this hierarchical nature of the language, and it is organized in a way that hopefully makes it convenient to go through and analyze, do something with it. So we are going to go with expressions today again, like last time, to keep things simple. And we'll start with kind of parsing and representing this expression here, but eventually, ultimately, what we are planning to get to and parse and execute is this, like factorials. But we are not going to go there today, just yet. Okay, so today I won't be showing any presentations because, well, we are just dealing with some technical thing related to a data structure, basically. So let's go over what we have in the AST. Like our language will have some basic kind of types of entities it will be comprised of. So we have expressions, we will have declarations, variable and functions, and we will have statements inside functions. And for each of those constructions we might have in our language, well, not might, for all those constructions we are planning to have in our language, we will get a node of the tree which is related to it. So let's start with the base. This is a list of everything which is going to be implemented in our language. So, as I said, lists are for like literally lists of things, like a list of declarations or a list of statements in a function or whatever, list of parameters potentially. This implicit cast thing, we will get to it later when we deal with types. Just for now, just disregard that. And okay, so what meaningful parts of the language are we dealing with here? So we have literal expressions, numbers, keywords like true, false, IDs for variables, parentheses, unitaries, binaries, function calls, and assign expressions for, well, to reassign different values to variables. Also, we'll have declarations for variables, for functions, and for function parameters. Because function parameters, when we get to functions, not today, spoiler, when we get to functions, I will show you the difference between a variable and a function parameter and why we need kind of different things for those. And also we will have 3 dedicated statements in our language. We will have returns, we will have if statements with else parts, and we will have while loops. So where it all starts, this one is for later, this class typed, so we will look at it maybe even today, but we'll look at it later. When we look at types, I will explain it better. But let's begin with the base class for our AST nodes. Every AST node will be inherited from this class. And every AST node will know what it is, basically, and provide the base with one of these tags. It's kind of like we have for tokens. When we have values and tags for AST nodes, we will also have tags associated with their classes, basically. Okay. So for the base class of our AST, we have some kind of a friend thing called builder here. This is what we are going to look at after I go through kind of our AST nodes, because the builder is one of the most important parts of it. And not much is going on here in the base node. It has this node kind thing, which represents its, well, basically it's every class inherited from it will provide a node kind. And it has a flag which indicates whether or not the node is valid. So if we have a syntax error, for example, the place where the error happened will be marked as invalid, and this invalid state will propagate all the way up. So let's say if we parse a big file of code in our language, and somewhere downstream in some function we find some syntax error, the entire thing will be marked as invalid, because after we parse the program, we are going to go and evaluate it, and we really don't want to deal with syntax errors at this point. So we will mark the entire program as invalid for one syntax error anywhere. And we will not, our evaluator will not deal with it. But that's for later. And yeah, you can ask the node if it's valid or not. And also, when we construct the tree, every child node will this is where the propagation of this invalid flag happens, basically. So we provide a child node we are about to attach to ourselves, and we mark ourselves as invalid if the child is invalid. I'll show you what it means in like today later. Okay, so the base class is like really simple, and we have this unfortunate virtual constructor here because class hierarchy, and we will be allocating those in memory, and we'll be using the base class pointers a lot. Okay, so this list thing is for lists, basically. And it will just have inside it a vector of pointers to AST nodes. So as you see here, so any list of things like, for example, again, function body, it will be represented as this class, this list, and it will have just a vector of child nodes in it. And yeah, we can ask it to give us access to its children, to the container with children. The next one node we will have is this error. Right? Yeah, this we have a tag for it. So we'll have the error node for syntax errors, and what it will give us, it will give us the kind of the position which token in our input caused us problems, and a custom message which we will provide to it when we construct it. Why do we need a node for errors? Like, why do we keep errors in the AST when syntax errors occur? Wouldn't it be different just to stop, right? So let's say we are going through our code, we are parsing it, we see something we don't like, and here we stop. Well, usually compilers do not work like that. If you have multiple errors in your program, and you try to compile it with something like, for example, Clang, if you're using C++, what you will get is not like a compilation aborted at the first error, and then you fix it, and then you restart, and you get aborted again, and so on and so forth. Usually you will get a list of errors in different parts of your program, and it will do its best to tell you every little place where an error occurred. And we are going to do that, basically. So whenever we see a syntax error in our code, we'll just create an error node, put it in place of a real node that would have been there otherwise, and we'll just continue. So this way, we can kind of mimic what real compilers do, and we will get a whole list of those syntax errors if there are multiple. So let's go over expressions next. Expressions, they will have an intermediate base kind of type from which all expressions will be inherited. And this class, this expression class, it just will just hold type information in it, basically. Why we need it is so that every expression has a type, because every expression will have a type in our system. And if you look here in its constructor, this base expression will invalidate itself if the type given to it is an error type. So we may have two different kinds of errors in our program. We may have syntax errors, or we may have semantic errors, like invalid type or whatever. So yeah, this also will cause our program to invalidate here. But as I said, types are for later, not today. All right, so next what we have? We have literal expressions. Those just hold a value, some kind of value. And we could kind of parse the value from the string. Like, let's say we have a number, like this one here, 12, whatever. So we could parse it and put it here in the literal expression as a value. But for our purposes, and not to load the parser with additional work, we are going to just save a token, which will tell us what kind of literal we are looking at. So it will tell us, oh, okay, it's an int or float or whatever, or true, false. And also it will give us a string representation of that literal. And so when we go to evaluate our code, then we will take the value and parse it. And we are kind of sure that the value stored in this literal expression can be parsed successfully because otherwise the lexer would have given back some invalid token or whatever. So we can only build a valid literal expression from a valid token. So that's okay. ID expression, it's going to be for variables. Variables we will cover in detail in an upcoming episode of this. And for this ID expression, it will have, again, a token called name. Well, it won't have a token itself. It will reference the place where this identifier was declared in our program. So when you are referencing a variable or a function, you can always ask it to give you the place where the declaration happened. This is decal, which is not defined here. Like if you look here, we have this forward declaration. I will show you what the declarations look like in a moment. Yeah, so every ID expression we will have, every identifier, to be usable, it should be defined beforehand. And when you see it in the AST, you will kind of be able to know instantly where it is defined and what it is. For parent expressions, parentheses, the thing is really simple. It will just contain a sub-expression, and that's all. And you might notice some pattern here, kind of, because every AST node class for it is extremely simple. That's because AST is just basically a dumb data structure. It has hierarchy, but it's just a tree. It doesn't have any complex logic by itself. We just build it, and then we use it in different parts of our language to do things with it. And one of the things I will show you today, we are going to look at the AST printer when we finish with that. Okay, so we have unaries, which have an operand. The type, again, every expression has a type, and it will have an operation. So this enum here, it's an enum operation. It's defined where we have the evaluator. Well, it is shared between the evaluator and the AST and parser to just keep one entity for operations. And it just represents whatever the operator of the unary expression is. So for unary, we will accept unary neg, which is the unary minus, unary plus, and the exclamation point, which is a logical negation or not. And yeah, this is a little bit of a crossover with a later part of the evaluation. Initially, I didn't have it there. I just had it here. Okay, let's look at the constructor. For unaries, again, we validate ourselves at this. If our operand is invalid, then the entire unary expression is also invalid. Okay, so after unaries, we have all kinds of binaries, which are also extremely simple. We'll just have like left operand, right operand, and the operator on the same enum we just looked at. Assign expression. Again, nothing new. It will just assign a value to a variable. So we have a reference to our variable. The right part of the assign expression kind of end. This operation here, it's for the future really, because right now we just have only one assign operation, so we just have equals sign. But if we decide to expand this, kind of like, let's say if we decide to add compound assignments like plus equals, minus equals, whatever, this operation thing here will be useful for us. Right now, it's always an assign operation. We are not going to be dealing with functions right now, but for functions, again, for function calls, when we get to them, we'll just have this kind of node where we will have the a reference to the function name, the ID expression, and arguments. Arguments are a list, just a list. Implicit cast just has one operand and the type which we are going to cast the operand to. And this one we need because if we use something like a binary expression for values of different types, we will need to first figure out their common type between them and cast, if needed, those operands to that common type. This is to make things easier for the evaluator, basically. Okay, so expressions also have declarations. Declarations also have types, names, and we have this decal class. Same as we had with expressions. And we will have declarations for variables, which will just have a name and an initializer. And we will have declarations for parameters. And the difference between a variable and a parameter is, well, first we will use different keywords to declare them, and parameters, function parameters, do not have initializers, only variables do. So look here. Like, here's the parameter. Like we use type name, and for variable we will use keyword var name equals whatever. And for function declarations, we will have a whole bunch of things, and we will get to those when we go into functions, just to not linger here for too long on this AST structure. And finally, we will have statements in our language. And for statements, we'll just have return, which has a return expression, which is optional. It can be empty, which means that we return nothing, or void. We will have an if statement, which has a condition, a body of the true branch, and an else a branch body as well. Those are lists, by the way. Well, not lists. They will be statements which potentially can be lists, compound statements. And for while loops, we will not have fors, we'll just have whiles, because if we need different things, we can also always add them, but for the purpose of this demonstration of how to make a language, I chose to use only one kind of loops to make things easier. For whiles, we will have a condition and a body, and all those constructions, they look pretty much the same as they look in C++, basically. Okay, and also we will have this concept here, which allows us to look at any type and determine whether or not it's a descendant from the base AST node. And we will be using this concept, well, in other parts of our language. Okay, so the structure of the ASTs is going to be like that. And now let's go and look at how we are going to actually build this AST. So the way we use our language, we have kind of static parts in it, which you want to keep. This thing is a semantic analyzer. We'll skip it today. It's going to be helping us with types and name resolution for variables and stuff. And this builder, we also have a builder for the AST. It's an AST builder, which we also want to keep. And well, basically until we are done with the entire program, because it will create and it will own the AST nodes. Every AST node ever created will be stored in the builder, because we need to have one place to own them all and to avoid kind of manual memory management. We'll just store those in builder and let it figure out how to delete them when time comes for them to be deleted. And our parser, on the other hand, there's no reason to keep it a static component. It will just, you can create a parser in place, use it, and throw it away. It doesn't have a state. It doesn't have any meaningful state. It's like a really sophisticated function, right? So you can call it and forget about it. And the parser will take the builder and semantic analyzer is dependencies, because it has a need to build the AST and it has a need to figure out identifiers as it goes. And this guy here, AST printer, we will look at it, how it's made. Okay, so for the builder, let's go to the parser and let's, I don't know, let's go to like literal expression here. So whenever we execute some grammar rule in our parser and we execute it successfully, we'll instruct the builder to create a node. And if you look everywhere, like in parent expression, for example, here we are successful in this line, and we will create a parent expression at this point. So the way this is going to work, we know that we are coming from an open parenthesis and consume it. We call export for the inner expression, whatever it might be. And then this is where, by the way, errors come into play. So if we do not see the closing parenthesis, we create an error. We say, okay, that's no good. So inside the parent expression itself, we will put an error, which will complain about closing parenthesis. I will show it to you. Okay, let's take a look at it right now. So let's say I put it here. If I start it, here we have it. So we have a parent expression. It has errors. And here we have this binary, this 11 times 9. And we have an error that expected the closing parenthesis. We expected the closing parenthesis and we didn't get it. Okay, so how the builder works is, if you look at here, you will see like we have a call to something called make parent in the builder. We will have a call to something make literal and we'll give it a token. Let's say we go to a unary expression. We'll say make unary op, which is operation. Like, where are all the parts, right? So in binary, we can make binary and say what kind of operator it is. So where are all these parts? So let's take a look at where all these parts are. I mean, to make a binary expression, we need left operand and right operand and operator, right? So here comes our builder. The builder, it has a storage for all AST nodes in our program. And this storage is going to be this. It's going to be a weird thing. It's a forward list of unique pointers to the base node. Like, why do we do it like that? Well, unique pointers are because we are dealing with a class hierarchy and we are carrying around pointers to the base class only. And a forward list is because it's cheap to insert new elements, and we will never have to traverse it in its entirety. So it's not the most memory efficient thing in the world because it has multiple allocations, but it will do because we don't have to really create that many nodes, and we will never traverse it, so it doesn't matter that we have random access to memory because the AST itself by its nature is random access to memory anyway. And we will also have something called a node container here. It's going to be just a vector of pointers to the base node of the AST. And this error message is just a stream view. Okay, so how we are going to use all those things? Like storage is kind of self-explanatory, I think. So we just create, whenever we have a need to create an AST node, we'll just put it there and use a pointer to it everywhere we need. And this, so it's storage, we'll just store nodes there. And node container thing, this one, which is called state. It acts kind of like a stack of sorts. So the way the builder works, we are instructed to create some kind of AST node. If this AST node does not require any child nodes, like it's a terminal, it's a literal expression, for example, the builder will just create it and put a pointer to this newly created node into this state. Just push it back to the vector. And it will do that every time, like it creates a node and pushes a pointer back to the vector. And then we go and create something like a binary expression, for example. And for a binary expression, we need two operands. So the builder, it will go into this vector, into this state, take two elements from the tail of it, and assemble a binary expression out of them. And it will then put this binary expression back. So this way, as we are building the AST, we don't have to keep track of created nodes in the parser or anyway. Like the builder itself will handle those. It will keep track of what nodes got created. It will put them into the state. It will remove them from the state and use them in other nodes when needed. So it has a bunch of those functions for creating different things. Let us just go and I think let's run it and see what it does, but we'll do with something simple. I don't know, 1 plus 2. So let's go and see how it's created. Last time I kind of broke my parser because we don't want to go into deep things like functions right now. But for expressions, it will work just fine. So we'll just deal with expressions for now, and our entire program is going to be a single expression. Well, let's go. Let's go and take a look how it works. So we are here in the program. So we start from the very top. We are basically here right now, before this one. So we'll just go into expression and we'll go all the way down our grammar in our recursive descent. So go to binary. It will take a while. So go deeper. I kind of explained how it works last time. So let's go to the unary for now. I know we won't go to the unary for now. We'll just go to the unary and put a breakpoint there. Eventually we will get there. So what's going to happen with our binary expression here? It will have this index, which it will increment as it goes recursively over the operation precedence, and it will in the end create the correct hierarchy based on which operation should be calculated first. We looked at it last time, so won't stop it here. So let's go to unary. Eventually, we will get here from the binary expression. This unary is still, we are looking at this number 1 here. So we ask the indexer to give us the next thing. It's 1. And we are checking kind of if it's a unary operation or not. If we had a -1, it would be a unary operator. Right now it's not, which is signified by this unknown value. So we'll just go to the postfix expression. Again, according to our grammar, we'll go to primary expression. And here in the primary expression, we are looking at 1, which is int number, which is an integer value token. So it's not, it's an int number. It's not an open parenthesis. It's a literal. So we go into the literal expression next. But here I want to kind of pause at the error thing, the entire error thing here. So our primary expression grammar rule, it accepts either an open parenthesis or a literal or an identifier. Everything else, if we came all the way down here, anything other than these 3, one of those is an error. And when we see an error, we kind of we act as if nothing happened. We will just create an error node here, say, unexpected token here, and just go along with, we will continue parsing. That's what I talked about at the beginning, when I talked about not wanting to abort on every error possible. Okay, so if we go to the literal expression, we'll extract the token. It's 1. And it's an int, and so we will go into the builder and make a literal expression there. And this make function here in the builder, it's a template, as you can see. It just calls constructors and then places things into the storage. So let's go here. Yeah. This is related to the type, so we are not going to look at it now. So yeah, we just create a node, we place it into this list of all AST nodes we have. So it's not empty, it has 1 element right now. And yeah, this is a pointer to the new node, and we'll push it into this state thing. And the state now has 1 element, okay? And the builder also has this root variable inside, which points to the last node created. Naturally, for the entire program, the last node created will be the topmost one. So we will just, when we finished with parsing, we'll just ask the builder to give us a new, the final node, the root basically of the entire program we have just parsed. Okay, so we initialize the root, and this state now has 1 element. Okay, so made a literal expression. We'll just go all the way back, and well, eventually we will get to the binary. Where's my binary? Here's my binary. So yeah, we've parsed the left part. We will just now go and proceed with the right part and all that stuff. We don't have to go over the entire thing. So eventually we will get into the builder and we are going to be ready to make the entire binary expression. So basically we are here now. So we went over the entire thing. Okay. And so if we take a look at what we have here, how can we do this in a good way? I hope you see it. Yeah, our state, never mind. We'll just see it when we get there. So our state right now will guaranteed to have two nodes because before going to the binary, the way the parser works, it will always in one way or another instruct our builder to create two nodes at least. Otherwise, it won't go and try to make a binary. So what we do is we have to take those operands back from the state. And if you look here, we extract the right-hand side operand first and left-hand side second. That's because the way we are treating our state as like a stack, and the left operand goes on the stack first, and the right operand, since it's parsed second, it will go on top of it. So kind of extract them in reverse order, which will be a common theme. Okay, so let's see what we have here. So in this state thing, by the way, I need to remove that because that's kind of it's code. In this state thing, we have two values, two pointers to two ints, 1 and 2, which we have parsed. So we take an item, the tail, the last back value, and we just pop back, remove it from our stack, from the state. So we do that with the right operand, we do that with the left operand, and now don't worry about that. This binary type, we'll look at it when we go to types. We figure out those types, and we just make a new binary expression. So if we go here into our list of nodes, we have 1, 2, and now we will have also here this binary expression node, which is easier to look at here. So we have kind binary expression, of course. We have left-hand side operand, which is 1, and we have the right-hand side operand, which is 2, and the operation is, of course, addition because we have a plus there. Now, in the state, which is empty, it won't be empty anymore. We will have our binary expression. Okay. So this is how the builder works. And it works this way for every kind of type of AST node we have. Like the idea is the same. It will assemble some nodes in the state. Then it will, when time comes, extract them all, assemble them into a new node, and replace all that bunch of nodes with the new node in the state. Or it will just add values of the pointers to nodes into the state if they are terminals. Okay. One thing I want to stop at here is this list. And the list looks kind of like weird because it's a bit of functional programming here, really. The way we create lists of values, since different different entities in the language require different handling when we organize them in lists. So declaration statements and things like parameters or arguments of function calls, they are a little bit different. But in terms of how we assemble them. But the basic logic for creating lists of nodes is kind of the same. Okay, so this is in the parser, and in the builder we will also have those lists. So basically what we do is we go over our syntax parsing rules and we count things we create. So by the end of a loop which creates a list of nodes, we will know exactly how many we must have. And every time we, on every iteration of our loop here, well, first we are looking for a token we can specify to stop parsing the list on. This is needed, for example, if we are going over a function body, we have an opening curly brace and we have a closing curly brace, and we can say, okay, so stop there. And also we have this list handler here. It's a function. It's a function, I'll show you here, which has, which accepts some type and returns a bool. And for every list of values, the handler will be different. So when we get to functions, I will show you the difference. Right now, I'm just saying that we have this weird logic of handling lists. And if this handler returns false, then we will not increase the list count. Yeah, because we might have situations when we do not kind of want to create a node and put it in the list and increase the count. And the node will not go to the builder. And in the builder, when we ask it to create a list of nodes, we'll just give it a count. And yeah, it will just go. It will just basically go the required number of elements back from the tail, extract this chunk of data, put it into a different kind of vector, and create an AST node out of it. Yeah, so here we'll just empty a whole bunch of nodes. Don't worry about that right now. We'll inevitably get to those lists later as well. All right, so yeah, for every kind of node, we have this make function here, which the parser calls. And those functions kind of take additional things from the outside if need be. So, for example, for an ID expression, we give it the declarator where it was. To create it for all kinds of unaries, binaries, and assigns, we have the separation thing going. For call expressions, we will just have like the function name followed by its arguments laying flat in this state. So we'll just get the arguments first and then the function itself. More on that when we deal with functions. Also can make variables, parameters, and For functions, again, they are a little bit tricky. Okay, but in any way, the basic idea behind the builder itself is you create stuff with it, you keep it in the builder's internal state, and then you extract those sub-items from the state, assemble bigger items, put them back, and this goes all the way up to the like the root of the program, at which point you will have consumed every node which you had in the state. Okay, now we are an hour into this already. We are an hour into this, and I want to ask you a question, if you don't mind. We talked about the structure of the AST and the builder. And what I had planned, kind of what I would like to talk about, is the AST visitor and an AST printer. Are you okay if I just go over those today, or are you toast and would prefer to bail right now? So if you guys don't write your opinion in the chat on that, I will just continue and go over the visitor and the AST printer. Need to get some food now. Well, oh, by the way, does anyone have any questions? Maybe continue. So it's like a voting, right? Okay, I think let's continue. Yeah, just scream in the chat if you've had enough. Okay, so for the AST, like why are we building it? Yeah, I mean it's fancy to have a good tree in your program, right? So it's all fine, but we are building it in order to eventually traverse it and do something. Like the most obvious thing is evaluate whatever is written there, like calculate all those binary expressions and so on. And for that, we need a visitor. So we can have something which we will feed our AST or a part of the AST, and it will go over it recursively and allow us to do something with that tree. So let's take a look at the visitor. I have the visitor right here and right off the bat. So we have concepts defined here. So why? Let's take a look at those first. Okay, so we will define two things which we need to consider and have in mind. So an AST node is considered visitable if given some visitor class, some object, and a pointer to that node. This visitor has a function called visit, which can accept a reference to the node. And also a node, an AST node, is considered previewable if given an object we will call a visitor, if it defines a function called preview, which can grab a reference to the node, and which returns a bool. Those are basically concepts which define objects for which we can enter. As we go over the AST, we can enter an object, look at it, do something, and when we after that we can leave. When we leave the object, we can also do something. So it will become clear right now. Don't worry. So we get kind of to our visitor thing finally. So we'll define a class called visitor. And if you are familiar with C++ and its dirty tricks, you probably know where this is going. So what we will have here is a template-based class which knows who is derived from it. This is called CRTP, or Curiously Recurring Template Pattern, where you have a base class, you inherit from it, and you tell it, hey, I'm derived from you. So why do we need it? Well, we need it because if the base class knows who is derived from it, then it can behave in kind of a polymorphic way without having stuff like virtual functions and runtime dispatch. It's all is going to be static. So the way our visitor works is we have an operator. So we inherit from the base class and we say, hey, I'm your descendant. And then what you do is you just define in your class for all those nodes you're interested in functions preview and visit. If you are not interested in a node, well, you just do not define functions for it. So let's go over how it works. Now, in our visitor here, we have those two functions. We have a function called visit, and we have a function called preview. And they get pointers at whatever's thrown at them, basically. But if you look at here, at how they are defined, so this visit here, it will be selected by the compiler only if this type of this node n is visitable. And this version will kind of like accept everything else, which is not visitable. So if your derived class, for example, for a literal, if your derived class looks like basically inherit from the base and defined a one single function visit for literal expressions and nothing else. If a literal expression goes here, this function will accept it. So it will go here and it will be dispatched to the derived class's visit function, which you have defined in the derived class. For every other type of node, it will just go here and do nothing. So, and for preview, the same thing. If a preview function is derived for a specific type of node, which happens to get into there right now, it will be dispatched to the derived class into its preview function. Otherwise, we just do nothing, return true. Why does the visit function not return anything, but the preview does? The visit function happens. If you look at the tree traversal, it's a depth first traversals. So you start at the root, You go down, 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 and then you go up, 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 and climb, basically. So for a binary expression, for example, you go into the binary expression, you go to the left branch of the left operand, and then you go up to the binary back, and then you go to the right operand and back. So this preview call for every node, it will happen when we enter. So let's say, again, we have a binary expression. So we enter the binary expression and we call a preview on it. If the preview returns true, we go to the left and then to the right. If the preview returns false, then we do not go left and right. We just skip whatever children the node has. This will be needed for the evaluator, like really needed. Right now, just keep in mind that the preview controls whether or not you go deeper into the tree from the current point. And the visit happens as you go up. So for our binary, proverbial binary expression, we get into it, called preview, decide whether or not we are going to go into its children, and then we call visit on it, and well, the process is recursive. It will continue. And those two functions, yeah, they give us a really flexible tool. So in descendants of our class, we can just define whatever we want and not everything. Like the advantage before, like, why it's better than virtual functions and stuff like that. So it doesn't provide too much hassle for us to use. Okay, and for every type of node we have in our AST, we will define those basic traversal logic functions here. Visit impl, I chose to call it. So the way it works, like for errors, literals, IDs, for terminal nodes which do not have children, we just go preview and visit. So we enter, leave immediately. Or compound nodes which have children, like for a parent expression, for example. We call preview and ask, okay, do we go deeper? If the preview returns true, by default it will always return true. We just go inside. So for the parent expression, we just go inside its internal expression, kind of. So this is our depth first visit. Kind of, we go down the tree, and here we are back, and we call visit on our current node. And it works the same for every node. Like for a unary, we go to the operand. For a binary, we go left, right, and so on and so forth. So for function call, for example, we go to callee and we go to arguments, and then we visit the function call itself. So yeah, it works the same way. Call preview, decide whether we want to go deeper, take parts, visit them, and visit our node on the way back. So those are visit impulse for everything. For everything we have, like for if statement, we will go condition, body, else. If we have else, we might not. And as you might notice, this visit root function here, it comes up quite a bit. And what it does, and by the way, we start with it here. So this operator parentheses is the entry point for our AST into the visit. So let's take a look at the visit root. And yeah, this is basically just a switch case. And that's why we have those node kinds, those tags we assign to every kind of node, because we do not have runtime type dispatch here. And we have to do kind of this static dispatch. Well, it's not really static, it's still a runtime thing, but well, it is what it is. We don't have virtual functions, we don't have polymorphism, so we're kind of faking it. Why we're doing it? Well, for two reasons. Well, first, every virtual function call implies, in some cases, really bad performance hit. And if they accumulate in your, when you go over the tree, it might be noticeable, especially for big structures. For smaller, nah. That's reason number one. And the reason number two, if we used virtual functions instead of template and this kind of static polymorphism thing, what we would have to do is either create all those visit and preview versions for every kind of node in our AST, for every possible node, and give them empty bodies and override only those we need in descendants. Or we would have to do that in the descendant classes, because then we could also create pure virtual functions, right? And make an interface kind of class out of this base visitor. But then guess what? Our derived classes would also become abstract interfaces if we did not kind of override everything. So yeah, we avoid cost of virtual calls, and we provide flexibility without virtuality to our derived classes. So that's basically how the visitor works. This function is called recursively every time. It takes the current node, let's say it comes from here or whatever, or here. It looks at what it is and casts it. This to function call is just a static cast, basically. It's a static cast to the type we tell it to cast to. So take the base node and just static cast to the correct derived class of the AST in the switch case. And we do it for every single node we come across, as we are going. And what it allows us to do is, let's start simple here. Let's say, I don't. Let's say we wanted only literals and we want to look at literals in our program only. So what we can do here, do plus lids, let's call it lids, public is the toy AST visitor, sorry, toy AST visit of lids. Unfortunately, though, all those nodes should be public nodes, visit functions for nodes. They need to be public, otherwise the base class won't have access to them. And we say void visit const is AST literal lit expert. And we say std cout literal expert value, which is a token, value, which is a string. And we go, just new line. Oops, sorry. I hope that wasn't too painful. I just hit my mic. And now we just go. Let's build a root. So watch what's going to happen. Put. So we have 12, 3. Let me do that. 12, 3, 2, 11, 9. Like our AST has all those, binaries and parentheses and so on, but we have just that easily created a a visitor which just prints out every value of every literal in our program. And for every other kind of nodes, for binaries and so on, we just have default behavior there. And now let's take a look at something more interesting, which is the AST printer. I think I showed it to you already. Come on, Control F5. As far as I can understand, we have a question. The visitor cannot modify the AST. How could I add additional information, type info, to the AST, or would there be a different approach? Well, the visitor, you could template the visitor by the node type also. Like here, if you go here and take a look at that, like we have node pointer, like const node star, that thing. You could add a template parameter, AST node n, and use like n here instead of const node. And depending on when you instantiate the visitor, you could give it a const or not const version. So you would write like class visitor, class something derived from visitor something, comma, just AST node, which would give you a non-const version of the node. And then here in those parts, like here you would use a like conditional thing based on const or not const. So it will make the visitor kind of more awkward and a little bit more complex, but it's doable. Yeah, it's doable. Using templates especially. And you could, you could use a visitor which respects constness. But in order to add type info and so on into the AST, we are going to be doing that, but that's not something a visitor is supposed to do, actually, because that's on creation of the AST, not on subsequent traversals. But yeah, if you decide to design things with kind of a mutable AST data, you could do that with the visitor. But yeah, let's continue. This is what our thing looks like. So yeah, it's a binary expression with another, so this minus is this minus here. This plus is, of course, the first plus. So it's a binary expression which has a left operand and a paren as the right operand. And let's take a look, how can we do that? And it looks kind of like what we have in Clang. If you looked at the Godbolt website, for example, whatever, and tried AST output in Clang, you would see something similar. Let's take a look at our AST printer right now. So again, yeah, we inherit from the visitor and we say, okay, we are an AST printer. And we will have a couple of things defined for that. The main thing being a vector in which we are going to, for every level of the tree we go down to, we are going to store the number of the children, of child nodes on that level. And this vector is, goodness, it's huge, is here. So this is a vector of child counts on every level of the tree. And this is needed for us to make indentations in the tree to those cute things which look really nice to look at. Okay, so let me just collapse those. This visitor, the printer of the AST, we are going to want to act on every node as we enter it, because we go top down kind of. So if we have a binary expression, we first print a binary expression and then its children, and not the other way around. So we will use our preview functions for that. So for every node, we will define a preview function in our visitor. And we will just do not define visit functions ever, because on the way back, we don't have to do anything. And they also are kind of typical and alike each other. Don't have variables just yet. Let's go and take a look at something like a binary. For simple nodes, we just print information about them. So let's say for literal, we print the word literal, we print its value, and in single quotes, we print the type, which we will go over later, and an end line, and return true, and we are done. For things like unary, for example, we of course have to print the operation which is used in the unary, and then we print its well, we do not print its children from like the function which deals with the node itself, because the visitor handles all the traversal stuff. But what we do for every node which has some children is we add an element into our vector of indentations, and we just specify, hey, I have one child, or for binary, hey, I have two children. And every time we enter a node, we call this indent function. So let's go over, let's, I don't know, try something simple, right? Let's go 1 + 2 and where is my operator? Here's my operator. So let's start the thing. Parser. We don't need the tilde. So here we are. We have our node. This is our binary expression. So it's it has a binary expression as the left operand. The left operand is 1 + 2, and the right operand is 3. So what do we do here? Indentation is clear, because we can reuse the printer. We don't have to create it every time a new, we'll just fill. just in case, clear the indentations. And we go into the base operator, into the base visitor operator, and we go to this visit rule then. So we have a binary expression. So just get here into the binary, cast it to binary, go to the binary and get into the preview, cast ourselves to the derived class, cast this to derived. And we get here into this preview of the binary expression. And let's go inside. So what this indent function does. It looks at our indentations vector, and if it's not empty, it just removes the last element, but only if the last element is 0. If the last element is something which is not 0, it will not remove it. I'll explain why. Okay, so right now indentations are empty. So we don't have any previous nodes which we might have printed. So for now, we just do nothing. We just return from here. And let's print the binary. So we have already printed the word binary and the opening quote kind of. We'll print the operator. So it's a plus. It's E plus. Yeah, see out the quote. Error mark, it will print has errors if the node is marked as invalid. Print the type, right now it's going to be int. Yeah. And it will put 2 into our indentations vector because the binary expression has 2 children. Okay, and return true. We go here. Since we return true, we go into the left operand of the binary. And again, this is it's a binary again. So we go here, cast ourselves. And that is our left operand. And let's go into the indent and see what happens. So indentations has 1 element of 2. This is what we push there for our top level binary expression. Which one? This one we have here. And currently it is not empty. Okay, so we entered this cycle to kind of remove all the zeros from the tail of this indentations vector. So right now our last element is 2. It's not 0, so we won't loop further. We'll go next. I'll just get out of the loop and go next. And here we have we take a reference to the back of the last element of our vector, and we will keep decrementing it until it becomes 0. And why we are doing that is to recursively print every kind of child level of this thing. So this loop here will go front to the end of all these indentations in case we get somewhere in the middle. And if we have reached like our current element, the last one, we will print basically one set of marks, and if we have not reached ourselves, we will print another set of marks. So right now we are current element we are standing at is not the element we have pushed back, if it makes sense. Okay, let's see what it does. Okay, and so here is where all those parts of the left line kind of printed. So if our element we are looking at is not the last element of the child, so if our indentations is still not 0, we will print this kind of pipe minus thing. And if we have reached 0, we will print this grave minus thing. So right now our child count is 1. So we will stdc out this. I'll show you how it looks. Yeah, this is the first child basically. And for the first child, since we have not reached the end, we'll just go and print this kind of line down. Okay, so we are going to print the left front of the binary at this point. Go here, and it's really awkward to explain. Like, if you look at it and debug it, I think it will become clear. But juggling all those, numbers of indentations in recursion is kind of, you might hear that it's awkward for me to explain. Okay, so we are printing the left operand of this binary right now. So we are printing this binary here. And now our indentations will have 2 elements. So what happens here? We have 2 binaries, right? So we have the top level binary and a left operand is also binary. For the top level binary, we have 1 child to print left. And for the inner binary, we still have 2 children to print left. And if we go into the left operand again, and the left operand is going to be this literal expert 1. So yeah, to the literal expert. Preview, arrived. And as you can see, it's kind of awkward to debug, really. Okay, so we are now looking at 1. Indentations is not empty. The last thing we have pushed into the vector is 2. Go, decrease it, and start iterating over it. So for the 0th element, it's the, what do you call it? The top level binary. We will just print this. So again, our count is not 0, so it's going to be child indent, and it's going to be this. So this binary has 2 children to go over still, and this binary has 1 children. So from this top level binary, we will kind of print this line all the way back to its last child. And for this binary expression, we will start a new line right here in a second. Okay, so continue. And then we have reached the child count we pushed for our current binary, the inner one. So print this. I'm somehow I broke it, I think. Yeah, so for the inner binary, we will again loop over all those indentations, and on every step we will see if it's 0 or not, and depending on if it's 0 or not, we will print this or this, basically. I'm sorry, it's really awkward to explain the way it works. But yeah, depending on how many children for every node we have left, we print different kinds of squiggles here. And we get this cute structure. And for all other kinds of nodes, we will perform the same thing over and over again. So you override a preview function for it. You write some information about the node itself. You say, okay, I have that many child nodes, and you return true from the preview. And the visitor, it will recurse over the tree and to print all those parts. My goodness, I tried to explain how this works several times, and every time I kind of do it in a really stupid way. Yeah, and I guess that's all I was planning for today. So we went over the visitor and we went over how these printer works. And yeah, my project here, my language is complete, kind of, but I'm showing you the parts as we go, not the entire thing. So it has things we are not going over just yet. But I will show you all those functions, what they do, as we get to more parts of the language when we parse them. Okay, any questions? I guess everyone's asleep. And I can understand you if you are. All right, so yeah, still awake, but yeah. Okay, so in that case, that's for today. It's going to be all, and next time we will do variables and types and semantics, entry into semantics. Okay. And after that, we will have functions and evaluation, and yeah, that's the plan. I guess 3-ish parts of the series we are going through in the future. All right, so thank you everyone for attending, and well, and have a good weekend. Bye, everyone.